Hello, and welcome to ZzScience. I'm glad you're here. Take a moment to relax, let your body settle, and let your mind slow down. If you'd like, you can share in the comments where you're listening from. For now, let's slow things down and begin. There's something deeply calming about looking up at the night sky. The stars have been there, twinkling in their ancient light for as long as humans have walked this earth. Our ancestors looked up at those same points of light, wondering what they were, creating stories about gods and heroes, trying to make sense of the vastness spread above them. And even now, with all our telescopes and satellites and scientific understanding, that sense of wonder hasn't faded. If anything, it's grown deeper, more profound, tinged with a question that sits quietly in the back of our minds whenever we gaze upward into the darkness. Are we alone? It's a simple question, really, just 4 words, but it carries with it an enormous weight, kind of cosmic loneliness that's hard to fully articulate. When you think about it, really think about it, the universe is so incomprehensibly large that it seems almost impossible that we could be the only ones here. There are more stars in the observable universe than grains of sand on all the beaches of Earth. Each of those stars might have planets orbiting around them, and some of those planets might be just the right distance from their star, in what scientists call the habitable zone, where liquid water could exist on the surface. Water, that essential ingredient for life as we know it. So if the universe is so vast, so filled with possibility, why does it feel so empty? Why haven't we heard from anyone out there? Why haven't they visited us, made contact, sent us a signal, left some trace of their existence that we could find? This puzzle has a name. Scientists call it the Fermi Paradox, named after the physicist Enrico Fermi, who supposedly asked his colleagues over lunch one day in 1950, "Where is everybody?" It's a good question, a haunting question in its way. And tonight, as you settle in, as you let your mind drift and wander among the stars, we're going to explore it together. Not in a frantic, urgent way, but slowly, gently, turning it over like a smooth stone in our hands, examining it from different angles, considering the possibilities. Because this question about alien life, about whether we're alone, touches on something fundamental about who we are as humans. It speaks to our curiosity, our loneliness, our hope, our place in the grand scheme of things. Let's begin by simply appreciating the scale of what we're talking about. The universe is old, unimaginably old. Scientists estimate it's about 13.8 billion years old. That number is so large, it almost loses meaning. Try to picture a billion of anything, and your mind probably can't quite grasp it. Now multiply that by nearly 14. That's how long the universe has been around, expanding and cooling, forming galaxies and stars and planets. Our own solar system, by comparison, is relatively young, about 4.5 billion years old. Earth formed from a disk of dust and gas swirling around the young sun, gradually clumping together through gravity, growing larger and larger until it became the planet we know today. For much of Earth's early history, it was a hostile, violent place. Asteroids and comets bombarded the surface. Volcanoes erupted constantly. The atmosphere was toxic, nothing like the oxygen-rich air we breathe now. But somehow, in all that chaos, life emerged. We're not entirely sure how. It's one of the great mysteries of science. Somewhere around 3.5 to 4 billion years ago, simple single-celled organisms appeared in Earth's oceans. These weren't anything complex, just tiny bits of organized chemistry that could reproduce themselves. But that was enough. That was the beginning. For billions of years, life on Earth remained simple. Just bacteria and other microscopic creatures floating in the oceans, slowly changing the planet. Those early organisms produced oxygen as a waste product, and over enormous spans of time, they transformed Earth's atmosphere into something that could support more complex life. Eventually, around 600 million years ago, more complicated creatures began to appear. Animals with bodies and shells and eventually bones. Life crawled out of the oceans onto land. Forests grew. Dinosaurs rose and fell. And finally, remarkably recently in geological terms, humans appeared. Modern humans, Homo sapiens, have only been around for about 300,000 years. And we've only had anything resembling technological civilization for a tiny fraction of that. A few thousand years of recorded history. A few hundred years of industrial technology. Less than a century of radio signals that could, theoretically, be detected by someone out there in space. When you put it in that context, we're newcomers. Late arrivals to a party that's been going on for billions of years. And that raises an interesting point. If intelligent life can arise on a planet, and if there are countless planets out there in the universe, then surely we're not the first. Surely, somewhere among those billions of stars and trillions of planets, life has emerged before. And if life emerged earlier than it did here, then it's had more time to develop, more time to advance, more time to spread across the cosmos. This is part of what makes the Fermi Paradox so puzzling. The universe is very old and very large. Even if intelligent life is rare, even if the odds are very much against it, the sheer number of possibilities should mean that it exists. And if it exists, and if it's had millions or even billions of years head start on us, then where are they? Why don't we see evidence of them everywhere we look? Some people imagine that aliens might already be here, that they've visited Earth, the past, or are observing us right now. This is the stuff of countless science fiction stories and conspiracy theories. Ancient structures like the pyramids are sometimes attributed to alien visitors, as if humans couldn't possibly have built such things on our own. Strange lights in the sky are interpreted as spacecraft. Every unexplained phenomenon becomes potential evidence of extraterrestrial contact. But when we look at these claims carefully, when we examine the evidence, it doesn't really hold up. The pyramids, magnificent as they are, show clear signs of human construction. We can trace the development of pyramid building through earlier, simpler structures. We found the tools the workers used, the quarries where they got the stone, even the villages where the laborers lived. We can understand how they did it with the technology they had available at the time. It required tremendous organization and effort, but it was well within human capabilities. As for UFO sightings and similar reports, most of them turn out to have mundane explanations. Weather balloons, aircraft, satellites, atmospheric phenomena, sometimes just outright hoaxes. That doesn't mean people are lying when they report seeing something strange. The human eye and brain can be tricked, especially when looking at distant lights in the sky under unusual conditions. We're pattern-seeking creatures, wired to find meaning and intention in things. And sometimes we see patterns that aren't really there. The question of whether aliens have visited Earth is actually testable in a scientific sense. If an advanced alien civilization had traveled here, they would have left evidence. Physical artifacts, traces of their presence, something we could examine and study. And despite decades of searching, despite thousands of reported UFO sightings and alleged alien encounters, we haven't found that kind of concrete, verifiable evidence. That doesn't absolutely prove aliens have never been here, but it does, suggest that the claims of visitation don't have the support that we'd expect if they were true. So instead, let's focus on the more interesting question. Not whether they've been here, but why they might not have come at all. Why the universe seems so quiet, so empty of other voices calling out across the darkness. One of the most fundamental challenges to interstellar travel, to any kind of contact between distant civilizations, is simply the enormous scale of space. We use the term space so casually that it's easy to forget what it really means. The distances between stars are so vast that they're difficult to comprehend, even when we use numbers. The nearest star to our Sun is called Proxima Centauri. It's part of a triple star system called Alpha Centauri, which you can see from the southern hemisphere as a single bright point of light. Proxima Centauri is the closest of the three, and it's about 4.2 light-years away. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. Light is the fastest thing we know of in the universe. Nothing can travel faster than light, according to our best understanding of physics. And yet, even moving at that incredible speed, it takes light over 4 years to reach Proxima Centauri from Earth. 4 years doesn't sound too bad, perhaps, but consider this. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reached speeds of about 160 kilometers per second as it fell toward the Sun. That's fast. Incredibly fast by human standards. But even at that speed, it would take the Parker Solar Probe about 7,000 years to reach Proxima Centauri. 7,000 years. That's longer than all of recorded human history. And Proxima Centauri is the closest star. Most stars are much, much farther away. Our galaxy, the Milky Way, is about 100,000 light-years across. It contains somewhere between 100 and 400 billion stars. Those stars are separated by enormous gulfs of empty space, most of them light-years apart from their nearest neighbors. And beyond our galaxy are countless others, separated by even more incomprehensible distances. The nearest large galaxy to ours, Andromeda, is about 2.5 million light-years away. When you start to internalize these distances, the silence of the universe becomes easier to understand. Even if there are thousands or millions of intelligent civilizations out there, they're so far apart that communication would be extraordinarily difficult. A radio signal sent from Earth travels at the speed of light. If we sent a message to Proxima Centauri, it would take 4 years to get there, and another 4 years for any reply to come back. That's 8 years for a single exchange of hello. And that's to the nearest star. For most destinations in our galaxy, we're talking about centuries or thousands of years for a message to arrive. Physical travel is even more challenging. As we've seen, even with our fastest spacecraft, a journey to the nearest star would take thousands of years. Now imagine trying to travel across the galaxy, or between galaxies. It starts to seem almost impossible. Not just technologically difficult, but practically impossible, given the constraints of physics and time. Of course, we can imagine that a very advanced civilization might develop faster spacecraft, might find clever ways to shorten journey times. Science fiction often invokes concepts like warp drives or wormholes, ways of cheating the cosmic speed limit. And while these ideas are fun to think about, and while they emerge from real physics in some cases, they remain purely theoretical. We don't know if they're actually possible, and we certainly don't know how to build them. Even if you could somehow travel at close to the speed of light, there are other problems. Space isn't completely empty. There are atoms of gas floating around, tiny grains of dust. At normal speeds, these don't matter. But if you're moving at a significant fraction of light speed, even a tiny particle becomes a devastating projectile. Imagine a grain of sand hitting you while you're traveling at half the speed of light. The energy of that impact would be enormous, enough to tear through any spaceship we can currently imagine building. You'd need shields, some way to deflect or absorb that constant barrage of cosmic debris. And then there's the problem of energy. Accelerating something to even a small fraction of light speed requires enormous amounts of energy. The faster you want to go, the more energy you need. And the relationship isn't linear, it's exponential. As you approach the speed of light, the energy requirements become astronomical. You'd need to carry fuel, which adds mass, which means you need more fuel to accelerate that mass, which adds more mass, and so on. It's a vicious cycle. Some have proposed using other methods, like solar sails that could be pushed by lasers, or harvesting energy from the vacuum of space itself. These are interesting ideas, and they might work for small probes, but scaling them up to transport living beings across interstellar distances presents challenges we haven't solved yet. Perhaps we will someday. Perhaps any civilization that survives long enough and develops sufficiently will figure out ways around these obstacles. But it's not obvious that it's possible, and it certainly isn't easy. So one possible answer to the Fermi Paradox is simply distance. Space is too big, the gulfs between stars too wide, the technical challenges too great. Intelligent civilizations might exist, but they're isolated from each other by the sheer scale of the universe, each one alone on their own little island, unable to bridge the vast oceans that separate them. But that's not the only possibility. Another interesting angle to consider is time. We've talked about how old the universe is, but we haven't really thought about what that means for the existence of civilizations. Life on Earth has been around for billions of years, but intelligent, technological life is brand new. We've only been broadcasting radio signals for about 100 years. In cosmic terms, that's nothing. A blink of an eye. Less than a blink. Now imagine another civilization somewhere out there in the galaxy. They might have arisen billions of years ago, developed technology, built cities and spacecraft, explored their solar system, perhaps even colonized other worlds. But here's the thing, they might be gone now. Civilizations might not last very long, at least not on cosmic timescales. They might destroy themselves through war or environmental collapse. They might fall victim to natural disasters, asteroid impacts, nearby supernova explosions. They might simply stagnate and decline, losing their technology over time. Or they might change in ways we can't predict, becoming something we wouldn't recognize as a civilization anymore. If intelligent life is both rare and brief, then the chances of two civilizations existing at the same time might be very small. Imagine the galaxy as a vast, dark field, and civilizations as fireflies that blink on for a moment and then fade away. The field might have many fireflies, but if they're never lit at the same time, they'll never see each other's light. We might be one of those fireflies, flickering briefly in the darkness, while the light from other fireflies hasn't reached us yet, or has already passed us by long ago. This is a melancholic thought in a way. It suggests that we might indeed not be alone, but we're alone in time rather than space. Other civilizations might have existed, might exist in the future, but we'll never overlap with them. We'll never know they were there, and they'll never know about us. Of course, we don't know how long technological civilizations typically last. We only have one example to work with, ourselves. And we're very young, still in the early stages of our technological development. We've already faced existential challenges, nuclear weapons that could destroy our entire civilization, climate change that could make our planet less hospitable, the risk of engineered pandemics or out-of-control artificial intelligence. These aren't abstract future concerns. They're real challenges we're dealing with right now. But we're also capable of remarkable things. We've eradicated diseases. We've begun to understand the fundamental laws of nature. We've left our planet, if only briefly, and walked on the moon. We have the capacity to recognize threats and work together to address them. The question is whether we'll be wise enough, cooperative enough, far-sighted enough to navigate the dangers and continue to thrive. If we do survive, if we figure out how to live sustainably and peacefully on our planet, then perhaps we can last for a very long time. Millions of years even. Long enough that the chances of overlapping with another civilization become more reasonable. Long enough that we might, eventually, develop the technology to travel between stars, or at least to send messages that could be received and understood. And this brings us to another aspect of the Fermi Paradox, the search for signals. If we can't physically travel to other stars easily, at least not yet, perhaps we can communicate across the distance using electromagnetic radiation. Radio waves, light. These travel at the speed of light, which is still very slow for interstellar distances, but it's the fastest option we have. Since the 1960s, scientists have been conducting searches for extraterrestrial intelligence, often abbreviated as SETI. The basic idea is simple. Use radio telescopes to listen for signals from space that might be artificial, that might indicate the presence of a technological civilization. Natural processes produce radio waves. The universe is full of them, but natural radio. Emissions tend to have certain characteristics, certain patterns and frequencies that we can recognize. An artificial signal, a deliberate transmission from an intelligent source, might look different. It might be narrower in frequency, more focused, perhaps modulated in ways that indicate information content. The challenge is that space is very large, and there are many frequencies to listen to, and we don't know where to point our telescopes. It's a bit like trying to find a specific conversation in a crowded room the size of a planet, when you don't know what language is being spoken or where the speakers are standing. You have to be very patient, very systematic, listening to one small patch of sky at a time, scanning through frequencies, hoping to catch something unusual. So far, after decades of searching, we still haven't detected any confirmed artificial signals from space. There have been a few intriguing moments, though. Brief anomalies that caught our attention. In 1977, a radio telescope in Ohio recorded a strong, narrow-band signal that lasted for 72 seconds. It was so unusual that the astronomer reviewing the printout circled it and wrote a single word beside it. Wow. Ever since, it has been known as the wow signal. But it was never heard again, despite many attempts to relocate it, reobserve it, or trace its origin. Without a repeat detection, without more data to study, we simply cannot say what it was. It might have been a transmission from an artificial source, or it might have been interference, or some natural phenomenon we don't yet understand. The absence of detection, however, doesn't necessarily mean there is nothing to find. Our search has been brief in cosmic terms, and we've examined only the tiniest fraction of the sky. It's a bit like dipping a single cup of water into the ocean, finding no fish inside it, and concluding that the ocean contains no life. The search must be far broader and deeper before strong conclusions can be drawn. There are also many assumptions built into the way we search. We look for radio signals because radio is a technology we know well, something we use, something we understand. But a more advanced civilization might communicate in ways we have not imagined or cannot yet detect. They might transmit using neutrinos, gravitational waves, tightly focused optical lasers, or some form of communication that, to us, would be indistinguishable from random noise. Their signals might be compressed, encrypted, or encoded in ways our instruments do not recognize as meaningful. And there is another possibility to consider. They may not be broadcasting at all. When we look at our own civilization, we can see this shift happening already. In the past, Earth leaked enormous amounts of radio energy into space. Television broadcasts, early radio transmissions, wide-beam radar systems. All of it spilled outward, unintentional and unfiltered. But as our technology has become more efficient, our leakage has diminished. We use fiber optic cables, focused digital signals, and communication methods that waste less power. Our accidental radio footprint has actually been shrinking, not expanding. A more advanced civilization might be even quieter still. Their technology might not leak into space in any detectable way. Or they may have chosen silence deliberately, perhaps out of caution, perhaps out of experience, perhaps because they simply have no desire to speak outward into the dark. This idea that advanced civilizations might remain intentionally quiet carries an unsettling implication. It suggests that the universe could be full of listeners, but very few speakers. A cosmos where many civilizations are alert, observant, cautious, but silent. This idea has been explored in science fiction as the dark forest, a vision of the galaxy as a place where broadcasting your presence might be dangerous, where survival means staying hidden. Whether that vision reflects reality, we cannot know. It is only a possibility, one among many. But it reminds us of something important. If other civilizations exist, their motives, their fears, their choices may be shaped by histories and perspectives far beyond anything we can imagine. There's another fundamental assumption we make when we think about alien life, and it's worth examining carefully. We tend to imagine that life elsewhere would be somewhat like life here, that it would be based on chemistry, on molecules and cells, that it would need energy and resources, that it would evolve and adapt to its environment. These seem like reasonable assumptions because they're based on the only example of life we know, life on Earth. But the universe is vast and strange, and it might be capable of producing things we haven't imagined yet. All life on Earth shares certain characteristics. We're all made of cells, built from the same basic components: proteins, nucleic acids like DNA and RNA, lipids that form cell membranes. We all use the same genetic code, more or less. We all need liquid water. We all process energy in similar ways. This uniformity suggests that all life on Earth descended from a single common ancestor, that first simple organism that emerged billions of years ago. We're all branches of the same tree. But does life have to be this way? Could there be other forms of life, based on different chemistry, using different solvents, operating under different principles? Scientists have speculated about such possibilities. Silicon-based life instead of carbon-based. Life that uses ammonia or methane as a solvent instead of water. Life that exists in the cold upper atmospheres of gas giant planets, or in the depths of subsurface oceans on icy moons. Life that doesn't require planets at all, but exists in interstellar clouds or the accretion disks around black holes. These ideas are highly speculative, and we have no evidence that such exotic forms of life actually exist. But they're not impossible, at least not as far as we know. Carbon is particularly good at forming complex molecules because it can bond with many other elements in many different ways, creating the intricate chemistry that life requires. But silicon, which is just below carbon on the periodic table, has some similar properties. Under the right conditions, could it serve the same role? Water is an excellent solvent, capable of dissolving many different substances, facilitating the chemical reactions that life depends on. But other liquids might work too, under different temperature and pressure regimes. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane on its surface. It's far too cold for liquid water, but the methane is abundant. Could some form of life exist there, adapted to those frigid conditions? We don't know, but it's an intriguing possibility that future missions might investigate. The point is that when we search for alien life, we might be looking for the wrong things. We might be searching for Earth-like planets in the habitable zones of sun-like stars, looking for signs of water and oxygen in their atmospheres, when life could exist in forms and places we haven't considered. This makes the search harder, but also more exciting. The universe might be even more full of surprises than we thought. Let's think about intelligence for a moment. When we ask whether aliens exist, we're usually asking about intelligent aliens, beings capable of thought and technology, civilizations we could potentially communicate with. But intelligence is just one possible outcome of evolution, and maybe not even a particularly common one. Life on Earth has been around for billions of years, as we've discussed. For most of that time, it was simple. Bacteria and other single-celled organisms dominated for over 3 billion years. Complex, multicellular life only appeared in the last 600 million years or so. Animals with brains and nervous systems are even more recent, and intelligence of the kind humans possess, the ability to use language, to create art and science and technology, is extraordinarily recent. A few 100,000 years at most. This suggests that while life might be relatively common in the universe, intelligent life might be much rarer. Intelligence requires a long chain of unlikely events. You need a stable planet with liquid water. You need the chemistry of life to emerge. You need that life to survive for billions of years, navigating environmental catastrophes and mass extinctions. You need evolution to stumble upon increasingly complex nervous systems. You need social structures that favor cooperation and communication. And you need the specific environmental pressures that reward intelligence over other survival strategies. On Earth, many organisms thrive without much intelligence at all. Bacteria are fantastically successful, occupying nearly every environment on the planet. Plants have colonized the land and the oceans. Insects outnumber us by unimaginable margins. Intelligence is energetically expensive. Brains require a lot of energy to maintain. Human brains, despite being only about 2% of our body weight, consume roughly 20% of our energy. That's a huge investment, and it only pays off if the benefits outweigh the costs. For humans, intelligence has been beneficial. It's allowed us to adapt to different environments without evolving new physical characteristics. We can survive in the Arctic and the desert, not because we've evolved thick fur or heat-resistant skin, but because we can make clothing and shelter. We can hunt prey much larger and stronger than ourselves using tools and cooperation. We can pass knowledge from generation to generation through language and writing, building on what came before. But you could imagine alien planets where intelligence never becomes advantageous enough to evolve, where the environment is so stable that simple organisms thrive without need for complex thought, where the available energy is so limited that the cost of maintaining a brain is prohibitive, where evolution takes different paths entirely, optimizing for different solutions to the challenges of survival. Even on Earth, intelligence has only evolved to human levels once, in one lineage of primates. Other animals are intelligent in their own ways. Dolphins and whales have large, complex brains. Elephants demonstrate problem-solving abilities and emotional depth. Crows can use tools and plan for the future. Octopuses, whose evolutionary lineage diverged from ours hundreds of millions of years ago, show remarkable cognitive abilities despite having brains structured completely differently from ours. But none of these species have developed technology or civilization as we understand it. This raises an interesting question. If we did encounter alien intelligence, would we recognize it? We tend to imagine aliens as being somewhat like us, perhaps with different physical forms, but with similar ways of thinking, similar motivations, similar concepts of communication and cooperation. But what if alien intelligence is truly alien, operating on principles we don't understand, perceiving the world in ways we can't imagine? Think about how different the subjective experience of an octopus might be from our own. Their nervous system is decentralized, with neurons distributed throughout their arms as well as in their central brain. Each arm can act semi-independently, processing information and making decisions without waiting for instructions from the central brain. What would it be like to think that way? To have your consciousness distributed across multiple semi-autonomous parts? We can't really know. We can't get inside an octopus's mind. Now imagine an alien intelligence that evolved in a completely different internet environment, with completely different sensory organs, a completely different evolutionary history. It might not have eyes as we understand them. It might perceive the world through echolocation or electrical fields, or by sensing chemical gradients, or through some method we haven't thought of. Its concept of time might be different. Its social structures might be different. The very way it processes information and makes decisions might be fundamentally unlike our own. If we encountered such a being, could we communicate? Would we even recognize that it was intelligent? There's a sobering thought experiment sometimes posed. Imagine if aliens had visited Earth millions of years ago, before humans evolved. They arrive, scan the planet, see abundant life, but no technology, no radio signals, nothing they recognize as intelligence. So they conclude the planet is uninhabited by intelligent life and move on. They never realize that, given a few more millions of years, one of those primate species will develop into something capable of building cities and spacecraft. Or imagine the reverse. We send a probe to an alien world. It scans for life, looks for certain chemical signatures, certain temperature ranges. It takes images of the surface, but it misses something. Maybe there's life there, but it's so different from what we expected that our instruments don't detect it. Maybe there's intelligence there, but it exists at a different scale or operates on different time scales than we do, so we don't recognize it. These possibilities are part of why the search for extraterrestrial life is so challenging. We're not just looking for a needle in a haystack. We're looking for something that might not look like a needle at all, in a haystack we're not sure exists, using tools that might not be capable of detecting what we're looking for, even if we point them in exactly the right direction. But let's return to the Fermi Paradox and consider some of the other proposed explanations. We've talked about distance and time, about the possibility that life is rare or intelligence is rare, about the challenges of detection and communication. But there are other ideas, some more speculative, some more disturbing. One possibility is what's sometimes called the Great Filter. This is the idea that there's some challenge, some difficult step in the development of life or civilization that most species fail to overcome. A filter that prevents most potential civilizations from ever reaching the point where they can spread across the stars. The Great Filter could be behind us. Maybe the hard step was the origin of life itself, that first emergence of self-replicating chemistry. Or maybe It was the development of complex cells with nuclei and organelles. On Earth, this took billions of years. Simple bacteria existed for eons before eukaryotic cells appeared. Maybe that transition is so difficult, so unlikely, that most planets never achieve it. If the great filter is behind us, then we're incredibly lucky to exist. But the future might be relatively safe. We've already passed the hardest test. But the great filter could also be ahead of us. Maybe lots of planets develop life, even intelligent life, but something prevents those civilizations from lasting very long or spreading very far. Maybe it's self-destruction through war or environmental collapse. Maybe it's some natural catastrophe we haven't encountered yet. Maybe there's some technological threshold that's inherently dangerous, something that every advancing civilization must face, and most fail to navigate safely. This is the darker interpretation of the Fermi Paradox. The silence of the universe might be a warning. It might mean that intelligent civilizations destroy themselves before they become visible on cosmic scales. If that's true, then the fact that we don't see evidence of aliens everywhere is ominous. It suggests that we might be approaching our own great filter, our own test that will determine whether humanity survives into the deep future or joins the countless other civilizations that might have risen and fallen in silence across the eons. Of course, this is speculation. We don't know if there is a great filter or where it might be. But it's a reminder that becoming a spacefaring civilization, spreading beyond our home planet, might be more difficult than science fiction often makes it seem. It might require not just technological capability, but wisdom, restraint, cooperation on a global scale. It might require solving problems like climate change, nuclear proliferation, artificial intelligence safety, challenges that test our collective intelligence and moral character. Then there's another class of explanations that's even more speculative, sometimes called the zoo hypothesis, or similar ideas. These suggest that aliens do exist. They might even be aware of us, but they're deliberately not making contact. Maybe they're observing us from a distance, like researchers studying animals in the wild, careful not to interfere or influence our natural development. Maybe there's some kind of cosmic rule or agreement among advanced civilizations, a prime directive borrowed from science fiction that prohibits contact with less advanced species until they reach a certain threshold of technological or social development. Or perhaps the explanation is more mundane. Perhaps advanced civilizations lose interest in exploration and communication. Once a species develops certain technologies, maybe they turn inward. Maybe they create virtual realities more interesting than the physical universe. Maybe they focus on uploading their consciousness into computers or modifying themselves into forms that no longer need physical bodies. Maybe they transcend in some way we can't understand, moving beyond the concerns of flesh and space and time into some other mode of existence entirely. These ideas are fun to think about, but they're very difficult to test or falsify. They remain in the realm of philosophy rather than science. Still, they remind us that our assumptions about what advanced civilizations would do or want might be completely wrong. We imagine them spreading across the galaxy, building megastructures, sending out fleets of starships, because that's what we imagine we might do if we had the capability. But we're young and limited in our perspective. A civilization 1,000,000 years older than ours might have goals and desires we can't even conceive of. There's also the possibility that we're simply not looking in the right way or at the right things. Most SETI efforts have focused on radio signals, but as we mentioned earlier, that might not be how advanced civilizations choose to communicate. Some researchers have suggested looking for other kinds of technosignatures, evidence of technology on cosmic scales. For example, a very advanced civilization might build structures around their star to capture more of its energy. The physicist Freeman Dyson proposed this idea back in the 1960s. He imagined that a growing civilization would eventually need more energy than their planet alone could provide. They might begin to construct solar collectors in space, eventually building enough of them to partially or completely enclose their star, capturing a significant fraction of its energy output. Such a structure, often called a Dyson sphere or Dyson swarm, would have a distinctive signature. The star would appear dimmer in visible light because much of that light would be intercepted by the collectors. But those collectors would heat up and radiate energy in the infrared. So a star surrounded by a Dyson sphere would look unusually bright in infrared wavelengths compared to visible light. Astronomers have searched for stars with this kind of unusual signature, and while they've found some interesting candidates, none have been confirmed as artificial structures. Most of the unusual stars have turned out to have natural explanations, like dust clouds or the aftermath of collisions between rocky planets. But this is a good example of how we might search for indirect evidence of alien civilizations. We might never receive a deliberate message, but we might be able to detect the side effects of their activities. Pollution in their atmosphere from industrial processes, changes to their planet's surface from large-scale engineering, unusual heat signatures from their cities or power plants, the light from their artificial illumination on the night side of their planet. These are all things that, with sufficiently powerful telescopes, we might be able to detect even if we can't communicate with the civilization directly. And this brings us to a genuinely exciting development in astronomy over the past few decades: the discovery of exoplanets. When I was young, we knew of only one planetary system, our own solar system. Planets around other stars were still theoretical, still speculation. We assumed they existed because it seemed strange that our sun would be the only star with planets, but we had no proof. That changed in the 1990s. Astronomers developed techniques sensitive enough to detect the tiny wobbles that planets induce in their parent stars as they orbit, or the slight dimming when a planet passes in front of its star from our point of view. The first confirmed exoplanet around a Sun-like star was discovered in 1995, and since then we found thousands more. As of now, we know of over 5,000 confirmed exoplanets, and the true number in our galaxy alone is likely in the billions. These discoveries have transformed our understanding of planetary systems. We've found planets of all sizes, from smaller than Earth to larger than Jupiter. Planets orbiting close to their stars, completing an orbit in just a few days. Planets in wide orbits, taking centuries to complete a single year. Planets around single stars, around binary stars, even around the remnants of dead stars. The diversity is astonishing. And critically, we found planets in the habitable zones of their stars, at distances where temperatures might allow liquid water on the surface. These are the planets most likely to harbor life as we understand it. They're not necessarily inhabited, of course. Being in the habitable zone is necessary, but not sufficient for life. The planet also needs an atmosphere, the right chemistry, protection from radiation, geological activity to cycle nutrients, and probably a dozen other factors we haven't fully identified yet. But it's a start. It tells us that the potential habitats for life are common, scattered throughout the galaxy. Some of these habitable zone planets are relatively nearby, astronomically speaking. Proxima Centauri, that nearest star we discussed earlier, has at least one planet in its habitable zone. It's called Proxima Centauri b, and it's only slightly larger than Earth. We don't know much about it yet, whether it has an atmosphere, whether it has water, whether it's actually habitable or just happens to be at the right distance. But it's there, and it's close enough that we might eventually be able to study it in detail. In the coming years and decades, new telescopes will allow us to examine the atmospheres of exoplanets, looking for chemical signatures that might indicate life. Oxygen is a good example. On Earth, oxygen is abundant in our atmosphere because photosynthetic organisms produce it. Without life constantly replenishing it, oxygen is reactive and would quickly be removed from the atmosphere through chemical reactions with rocks and gases. So, finding oxygen in an exoplanet's atmosphere, especially in combination with other gases like methane that don't naturally coexist in equilibrium, might suggest that life is present. This kind of detection would be momentous. It wouldn't tell us that intelligent life exists on that planet, just that some form of life, even if only microbial, is present. But it would answer one of the fundamental questions. Does life exist elsewhere, or are we alone? And if we find that life has emerged independently on another world, that would suggest that life is not rare, that the universe might be full of it. The implications would be profound. Of course, even if we detect signs of life on an exoplanet, actually making contact would still be extraordinarily difficult, given the distances involved. A planet 10 or 20 or 100 light-years away is close by galactic standards, but still represents an enormous gulf. Any message we send would take years to arrive, and we'd wait just as long for a response. Physical travel would be even more daunting. But perhaps that's okay. Perhaps the value isn't in making contact, but simply in knowing. Knowing that we're not alone, that life exists elsewhere, that the universe is richer and more vibrant than a cold, dead void. That knowledge alone might change how we see ourselves and our place in the cosmos. It's worth considering what finding alien life, even simple microbial life, would mean for us psychologically and philosophically. For all of human history, life on Earth has been the only life we know of. We've been alone, at least as far as we can tell, with no evidence that anyone else is out there. This uniqueness has shaped our religions, our philosophies, our sense of meaning and purpose. Many human cultures and religions place humanity at the center of creation, as the special creation of a divine being, made in the image of God. The discovery of alien life wouldn't necessarily contradict religious belief. Many theologians have thought about this possibility and found ways to reconcile it with their faith. But it would certainly require some adjustment of worldview. We wouldn't be the only children of creation. We'd be one species among potentially many, all sharing the universe. From a secular perspective, the discovery of alien life might be humbling, but also strangely comforting. Humbling because it would confirm that we're not special, not unique, not the pinnacle of creation. We're just one outcome of natural processes that occur throughout the universe. But comforting because it would mean we're not alone. Somewhere out there, under alien skies, other forms of life are pursuing their own existence, facing their own challenges, experiencing their own version of what it means to live. And if we're not alone, if life is common, then perhaps intelligence is not unique to us either. Perhaps somewhere, around some distant star, another civilization is asking the same questions we're asking, looking up at their night sky and wondering if anyone else is out there, listening for signals, hoping for contact. The thought is strangely moving. We might be separated by vast distances, unable to communicate or ever meet, but we'd be connected by our shared curiosity, our shared wonder at the universe we inhabit. When we think about the search for extraterrestrial life, it's easy to focus on the big questions, the dramatic possibilities. But there's something to be said for starting smaller, closer to home. Before we worry about civilizations across the galaxy, perhaps we should consider whether life exists elsewhere in our own solar system. The search for life doesn't have to begin light years away. It might begin right here, on worlds we can actually visit with our spacecraft. Mars has always been the most tantalizing possibility. It's our neighbor, a cold desert world that looks barren and hostile from a distance. But the more we study Mars, the more we realize it wasn't always this way. Billions of years ago, Mars was a very different place. It had a thicker atmosphere, warmer temperatures, and most importantly, liquid water flowing across its surface. We can see the evidence of this ancient water everywhere on Mars. There are dried-up river valleys, ancient lake beds, minerals that only form in the presence of water. Mars once had the conditions that, on Earth, gave rise to life. So the question naturally arises, did life emerge on Mars during that wet, warm period in its early history? And if it did, what happened to it when Mars lost its atmosphere and dried up? Could some form of life still persist there, hidden beneath the surface where conditions might be more hospitable? We've sent many spacecraft to Mars over the decades, orbiters and landers and rovers, each more sophisticated than the last. They found intriguing hints, but nothing definitive. Some of the rovers have detected organic molecules, carbon-based compounds that could be the building blocks of life or the remnants of past life. But they could also be formed by non-biological processes, so we can't be certain. There's also the matter of methane in Mars's atmosphere. Methane is interesting because it's a gas that breaks down relatively quickly under ultraviolet light from the sun. If we detect methane on Mars, something must be producing it to replenish what's being destroyed. On Earth, most atmospheric methane comes from biological sources, from bacteria and other organisms. But methane can also be produced geologically, through reactions between rocks and water. So the presence of methane on Mars is intriguing, but not proof of life. The truth is, we haven't yet done the kinds of experiments that would definitively detect life on Mars if it's there. Our current spacecraft are looking for habitable conditions and signs that life might have existed in the past. But they're not specifically designed to find living organisms. That might change with future missions. There are plans to send more advanced rovers, equipped with instruments that can analyze soil samples in greater detail, looking for the chemical signatures of metabolism or the physical structures of cells. And eventually, we plan to bring samples back from Mars to Earth, where they can be studied in laboratories, with equipment far more sophisticated than anything we can send to Mars. This sample return mission is years away, but it represents perhaps our best chance of answering the question of whether life ever existed on Mars. If we find even a single fossilized microbe in those samples, it would be one of the most important scientific discoveries in history. But Mars isn't the only place in our solar system where life might exist. In fact, some of the most exciting possibilities aren't on planets at all, but on moons. Several of the large moons orbiting the outer planets, Jupiter and Saturn, have conditions that might support life. Europa is one of Jupiter's moons, and from a distance it looks like a ball of ice. Its surface is smooth and bright, covered in a frozen shell of water ice. But beneath that ice, there's strong evidence that Europa has a global ocean of liquid water. The ice shell might be tens of kilometers thick, but underneath, warmed by tidal forces from Jupiter's gravity, there's an ocean that could be deeper than all of Earth's oceans combined. Water is the key ingredient for life as we know it, and Europa has lots of it. But life also needs energy and nutrients. Could Europa's ocean provide those? We think it might. The ocean is in contact with a rocky seafloor, and the tidal heating that keeps the water liquid could also drive volcanic activity on that seafloor. On Earth, we found thriving ecosystems around deep-sea hydrothermal vents, places where hot, mineral-rich water spews up from cracks in the ocean floor. These ecosystems don't depend on sunlight at all. They're powered by chemical energy from the vents. Bacteria harvest that energy, and other organisms feed on the bacteria. If similar vents exist on Europa's seafloor, they could support similar ecosystems. Life that evolved in the darkness, never seeing the sun, sustained entirely by the geological energy of its moon. It's a strange thought, but it's not implausible. The ingredients are there. The question is whether life actually took advantage of them. Enceladus, one of Saturn's moons, is another intriguing possibility. Enceladus is much smaller than Europa, but it too appears to have a subsurface ocean. We know this because Enceladus has geysers, jets of water vapor and ice crystals that spray out from cracks near its south pole into space. The Cassini spacecraft flew through these plumes and analyzed their composition. They contain water, salt, and organic molecules. The ocean they come from is in contact with a rocky core, and the water chemistry suggests that reactions are occurring between the water and the rock. Reactions that could provide energy for life. These ocean worlds, Europa and Enceladus, and perhaps others, represent a fascinating frontier in the search for life. Their environments completely unlike Earth's surface, dark and cold and isolated, but they have the essential ingredients. And if life can exist there, it would tell us something profound. It would suggest that life is not limited to planets like Earth, not limited to worlds with sunlight and atmospheres. It can exist in places we never would have thought to look. And if our solar system has multiple independent origins of life, if life arose not just on Earth, but also on Mars or Europa or Enceladus, then life might be incredibly common throughout the universe. That's a big if, of course. We don't know yet. We need to explore these worlds more thoroughly. There are missions in development to study Europa and Enceladus in greater detail. Some of these missions might even attempt to land on the surface and drill through the ice, or to sample the plumes more comprehensively. These are difficult, ambitious missions, but the potential payoff is enormous. Even our own moon might have clues about life's distribution in the solar system. The moon itself is lifeless, a dry, airless rock with no atmosphere and extreme temperature swings. But early in the solar system's history, during a period called the Late Heavy Bombardment, asteroids and comets were constantly crashing into the inner planets and moons. Some of those impacts were violent enough to blast fragments of rock from one world into space, where they could eventually fall onto another world. This means that rocks from Mars have landed on Earth, and rocks from Earth have landed on Mars. We've actually found Martian meteorites on Earth, and we've studied them in laboratories. If life existed on early Mars, and if a piece of Mars containing that life was blasted into space and eventually landed on Earth, could that life have survived the journey? Could life have spread between planets this way? It's not impossible. Some bacteria can survive in space for extended periods, protected inside a rock. If they arrived on a world with the right conditions, they might be able to establish themselves. This process is called panspermia. And while it's speculative, it's not ruled out by what we know about physics and biology. If panspermia occurred within our solar system, then life on Earth and life on Mars might share a common origin. They might be distant cousins, descendants of the same ancestral microbes. This would be fascinating to discover, but it would also complicate the question of how common life is in the universe. If we find life on Mars, and it turns out to be related to life on Earth, we haven't actually found two independent origins of life. We found that life spread between neighboring planets in the same solar system. That's interesting, but it doesn't tell us whether life emerges easily or whether Earth's life is unique. On the other hand, if we find life on Mars and it has a completely different biochemistry, a different genetic code, different amino acids or nucleotides, then we'd know for certain that it arose independently. That would be strong evidence that life emerges whenever conditions are suitable. And that would have profound implications for the prevalence of life in the universe. Let's step back for a moment and think about what it would take for a civilization to become truly spacefaring, to spread beyond their home planet and colonize other worlds. This is relevant to the Fermi Paradox, because if intelligent life is common, and if spacefaring civilizations tend to expand and colonize, then we'd expect to see evidence of that expansion. We'd expect to see a galaxy teeming with settlements and industry and communication networks. But we don't see that. So either intelligent life is rare, or civilizations don't tend to expand, or something prevents them from doing so. Humans have dreamed about space colonization for a long time. We've imagined bases on the Moon and Mars, rotating space stations that provide artificial gravity, generation ships that carry passengers on centuries-long journeys to other star systems. These ideas are inspiring, and some of them might be technologically feasible, given enough time and resources. But they're also enormously difficult, far more difficult than science fiction often portrays. Consider what it would take to establish a self-sustaining colony on Mars. First, you need to get there, which requires a journey of several months. You need to bring everything the colonists will need to survive: food, water, air, shelter, tools, medical supplies. Or you need to bring equipment that can produce those things from local resources, which is possible but technically challenging. Mars has some resources we can use. Its atmosphere is mostly carbon dioxide, which we can split to produce oxygen. There's water ice in the soil and in polar caps, which we can melt and purify. We can potentially grow food in greenhouses using Martian soil, though we'd need to add nutrients and ensure the soil doesn't contain any toxic compounds that would harm the plants. But even with all that, living on Mars would be harsh. The atmosphere is too thin to breathe and doesn't provide much protection from radiation. The surface temperature averages around -60 degrees Celsius. Dust storms can engulf the entire planet and last for months. Colonists would need to live in sealed habitats, venturing outside only in spacesuits. They'd be entirely dependent on their technology for survival. A single major equipment failure, a breach in a habitat wall, a failure in the life support systems could be catastrophic. And beyond the technical challenges, there are biological and psychological ones. The lower gravity on Mars, about 38% of Earth's, would have effects on the human body. We know from studies of astronauts in space that microgravity causes muscle atrophy, bone loss, changes in the cardiovascular system. Partial gravity like Mars might be better than microgravity, but we don't know how much better. It's possible that humans born on Mars would develop differently, growing taller perhaps, with weaker bones and muscles, unable to ever visit Earth without severe health consequences. Then there's the psychological challenge of living in a confined, isolated, hostile environment, far from Earth, with no possibility of quick return. Antarctic research stations give us some insight into this. People who spend winters in Antarctica, isolated for months in small groups, sometimes experience psychological stress, depression, interpersonal conflicts. And they know that rescue is possible if something goes wrong. Mars colonists wouldn't have that assurance. None of this means that Mars colonization is impossible. Humans are remarkably adaptable, and we've survived and thrived in harsh environments throughout our history. But it does mean that colonization is hard, risky, and expensive. It requires enormous commitment and resources. And if it's this hard for us to colonize the next planet over in our own solar system, how much harder would it be for any civilization to colonize worlds around other stars? Interstellar colonization faces all the challenges of Mars colonization and adds the problem of distance. A journey to another star would take not months but decades, centuries, or millennia, depending on the speed you can achieve. The colonists would need a completely self-sustaining ecosystem, a miniature world that can support them for generations. They'd need to deal with the cosmic radiation in interstellar space, the psychological effects of such a long journey, the social and political structures that would emerge in an isolated community with no contact with home. And if they succeed in reaching another star system, they'd need to find a suitable planet or moon to colonize, then face all the same challenges of establishing a foothold in a new environment. It's a daunting prospect, perhaps more daunting than any challenge humanity has ever faced. Some people argue that because it's so difficult, interstellar colonization might never happen, or might be so rare that the galaxy remains largely unpopulated even if intelligent life is relatively common. Others argue that technological advancement will eventually make it feasible, that a sufficiently advanced civilization could build spacecraft capable of relativistic speeds, or generation ships large enough to be comfortable homes for their passengers, or could even find ways around the limitations of physics that we currently think are absolute. We don't know which view is correct. We can't know until we try, or until we encounter someone else who has tried. But the difficulty of space colonization is one possible explanation for the Fermi Paradox. Maybe civilizations do arise, but they remain bound to their home planets, or at most, their home solar systems. The challenges of interstellar expansion are simply too great. There's an interesting variation on this idea, sometimes called the sustainability filter. It suggests that while technological civilizations might arise fairly often, most of them fail to develop sustainable relationships with their environment. They overexploit their planet's resources, damage their ecosystem, render their world less habitable. This leads to collapse or extinction before they can develop the capability to spread to other worlds. Earth's history shows that civilizations can indeed collapse. The archaeological record is full of societies that once thrived but then fell into decline, sometimes quite suddenly. The reasons vary. Environmental degradation, climate change, warfare, disease, economic problems, or combinations of these factors. Usually the people survived in some form, their descendants founding new societies. But the particular civilization, its cities and institutions and culture, ended. Could the same thing happen to our global technological civilization? It's an uncomfortable question, but an important one. We're facing environmental challenges, climate change most prominently, that could have severe consequences if not addressed. We have weapons capable of destroying our civilization in a matter of hours. We're developing artificial intelligence and biotechnology that, if misused, could pose existential risks. Whether we navigate these challenges successfully will depend on our wisdom, our cooperation, our ability to prioritize long-term survival over short-term gains. If we fail, if our civilization collapses before we establish self-sustaining settlements beyond Earth, then we're vulnerable to extinction. A large enough catastrophe, an asteroid impact or a supervolcano, or a runaway climate shift could wipe out humanity entirely. And if this pattern is common, if most civilizations destroy themselves or collapse before becoming truly spacefaring, then the galaxy might be full of ruins. Dead worlds where life arose and even became intelligent, but couldn't survive its own success. That's a dark thought, and there's no way to know if it's true. But it's a reminder that the Fermi Paradox might not be just an abstract puzzle. It might be a warning, a cosmic lesson written in the silence of the stars. If we want to meet our neighbors, we first have to ensure that we survive long enough to do so. On the other hand, there are reasons for optimism. Humans have shown remarkable resilience and adaptability throughout our history. We've survived ice ages and droughts and diseases. We've spread across the entire planet, adapting to every environment from tropical rainforests to Arctic tundra. We've developed sophisticated tools and technologies, learned to cooperate in large groups, created art and science and philosophy. We're capable of great things when we work together, and we're increasingly aware of the challenges we face. Climate change is widely recognized as a serious threat, and efforts are underway to transition to sustainable energy sources. There's growing international cooperation on issues like arms control, disease prevention, and space exploration. We're thinking about the long-term future in ways that previously generations didn't always do. Perhaps we'll succeed. Perhaps we'll navigate the challenges, establish sustainable societies, and begin the long process of spreading beyond Earth. First to the Moon and Mars, then to the asteroid belt and the outer solar system, eventually perhaps to other stars. It won't be easy or quick. It might take centuries or millennia. But if we manage it, we'd be answering the Fermi Paradox in our own way, becoming one of the civilizations that others might one day detect. And who knows? Maybe we're early. Maybe the universe is only now reaching the stage where technological civilizations commonly arise. Stars and planets take time to form. The first generation of stars didn't have planets like ours because they lacked the heavier elements that planets require. Those elements were formed later, in the nuclear furnaces of massive stars and scattered into space when those stars exploded as supernovae. It took generations of stars, living and dying, to enrich the galaxy with carbon and oxygen and iron and all the other elements that make up rocky planets and living organisms. Our Sun is a relatively late generation star, formed from gas clouds that had been enriched by earlier supernovae. Planets like Earth couldn't have formed in the early universe. They had to wait for the right chemical ingredients to be available. And then life had to emerge and evolve, which on Earth took billions of years. So maybe most habitable planets in the galaxy are similar in age to Earth, give or take 1 billion years. Maybe we're not late to the party. Maybe we're among the early arrivals, and the galaxy will become much more populated in the future. This would mean that the silence we observe now is temporary. In another 1 billion years, the galaxy might be bustling with civilizations. But we wouldn't be around to see it, at least not as we are now. Humanity as a species might evolve into something different, or spread out so much that we're no longer a single, unified civilization, or transcend biology entirely. The future is deeply uncertain. But uncertainty isn't the same as hopelessness. It means the future is still being written, still open to many possibilities. What we do now, the choices we make, the values we uphold, will shape how that future unfolds. In a sense, the question of whether aliens exist and why we haven't met them connects to deeper questions about who we are and who we want to become. There's a strange kind of comfort in the silence of the universe, even as it confuses us and leaves us full of questions. When we look up at the night sky, when we think about the vastness of space and the absence of clear signals from other civilizations, it can make us feel small and perhaps a little alone. But there is another way to see it. This silence, this apparent solitude, gives us room to grow. It gives us space to discover who we are without interference, to make our own mistakes, to write our own story at our own pace. There is a certain freedom in that, and alongside the freedom, a sense of responsibility. Throughout human history, whenever different civilizations on Earth encountered one another for the first time, the outcomes were complicated. Sometimes there was peaceful exchange, trade, shared knowledge, new ideas spreading across cultures. But often, especially when one civilization was much more powerful than the other, contact brought exploitation, conquest, disease, and suffering. The stronger group imposed its values, the weaker group paid the price. It's understandable then that some people worry about what first contact with an alien civilization might mean. If they were more advanced, technologically or intellectually, would we be vulnerable? This concern is one reason some scientists urge caution about broadcasting our presence into space. Why announce ourselves, they ask, when we don't know who might be listening, or what their intentions might be? And yet, that fear may not tell the whole story. The vast distances of space create their own kind of protection. Even if a distant civilization detected our signals, even if they wanted to reach us, traveling here would demand extraordinary time and effort. By the time they arrived, centuries or even millennia might have passed. Humanity would no longer be what it is today. We would have changed, advanced, adapted, perhaps spreading farther into our own solar system. It is also possible that any civilization capable of crossing interstellar space might not be interested in conquest at all. The kinds of resources found on Earth, metals, water, raw material, exist throughout the cosmos. There is nothing materially unique here that would justify such a monumental journey simply to take it. The only truly unusual thing about Earth is life, especially intelligent life. And if a civilization had come all that way to study life, it would make sense that they would want to observe carefully, rather than destroy or disrupt. Much like we attempt, however imperfectly, to study fragile ecosystems or endangered species without harming them. Of course, all of this remains speculation. We don't know what alien motivations would be like, or whether their idea of motivation would resemble ours at all. They might be curious, indifferent, benevolent, or something beyond our imagination entirely. The point is simply this: the silence of the universe, however mysterious, is not necessarily something to fear. It gives us time and space to develop on our own terms. Now, let's think for a moment about communication itself. What would it truly mean to make contact with another intelligent species? In fiction, the process often seems simple. A message arrives. We decode it. We reply. Soon we're exchanging ideas, comparing knowledge, perhaps even sharing culture. But real communication would almost certainly be far more complex. Language, even here on Earth, is deeply shaped by biology, senses, environment, culture, and history. The words we use, the ideas we are able to express, are woven into what it means to be human. An alien species would have evolved under entirely different conditions, different bodies, different senses, different pressures for survival. Their way of communicating might not resemble language as we know it at all. What we call conversation might be, to them, something unrecognizable. And that uncertainty, that vast difference, reminds us just how small our window of understanding truly is, and how much mystery still remains, quietly waiting in the dark. They might not use sound at all. They might communicate visually, through color changes in their skin like some cephalopods on Earth, or through electrical signals, or chemical signals, or something we haven't thought of. Even if they do use sound, their hearing might be sensitive to different frequencies than ours. What we perceive as noise might be their speech, and vice versa. And the concepts they express might be fundamentally different from ours. Think about how difficult it can be to translate between human languages. Some words and phrases don't have direct equivalents. The nuances get lost. Jokes and poetry are especially hard to translate because they rely on wordplay and cultural context. Now imagine trying to translate between human and alien, with no shared biology, no shared evolutionary history, no shared cultural touchstones. Mathematics is often suggested as a universal language, something that any technological civilization would understand. The basic laws of physics and mathematics should be the same throughout the universe. Prime numbers are prime numbers. Pi is pi, regardless of who's doing the calculating. So perhaps we could communicate mathematical concepts, build up from simple arithmetic to more complex ideas, eventually establishing enough common ground to attempt more sophisticated communication. This approach has been used in designing messages for potential aliens. The Arecibo message, sent from a radio telescope in Puerto Rico in 1974, was a short radio transmission aimed at a globular star cluster about 25,000 light-years away. It contained information encoded in binary, including the numbers 1 through 10, the atomic numbers of elements important for life, the structure of DNA, a stick figure representation of a human, and a diagram of our solar system. The message was more of a demonstration of human capability than a serious attempt at communication. The target star cluster is so far away that even if someone receives the message and immediately responds, we won't get their reply for 50,000 years. But the message illustrates an approach. Use simple mathematics and physics to establish common ground, then build up to more complex information. Even with this approach, there's no guarantee of understanding. The aliens would need to recognize the message as artificial, decode the structure, interpret the symbols correctly, and understand what we're trying to convey. Each step requires assumptions about what they know and how they think. It's entirely possible that they could receive our message and have no idea what it means, or misinterpret it completely. And that's just the technical challenge of encoding and decoding information. The deeper challenge is semantic. Even if we can exchange information, can we truly understand each other? Can we share ideas and feelings and perspectives? Or are we fundamentally too different, our minds shaped by such divergent evolutionary paths that mutual understanding is impossible? There's a concept in philosophy called the problem of other minds. How do I know that other people actually have conscious experiences like I do? I can observe their behavior, hear them describe their feelings, see them respond to stimuli. But I can't directly access their subjective experience. I can't know what it's like to be you, to see through your eyes, to feel your emotions. I assume you have an inner life similar to mine because we're the same species with similar brains and similar biology. But I can't prove it. This problem becomes even more acute with animals. Does a dog have subjective experiences? Most people would say yes. The dog seems to feel happiness when playing, fear when threatened, affection toward its owner. But what about a fish, an insect, a plant? At some point we become uncertain. The further removed an organism is from us biologically, the harder it is to say whether it has anything like consciousness or subjective experience. Now imagine an alien intelligence with a completely different evolutionary history. Could we ever know what it's like to be them? Could they know what it's like to be us? We might be able to exchange information, describe our environments and technologies and discoveries. But could we truly understand each other's perspectives, our hopes and fears, our sense of beauty or meaning or purpose? Maybe not. Maybe the gulf between species that evolved on different worlds would be too wide to bridge. Or maybe understanding would be possible, but require immense effort and patience, a willingness to set aside our assumptions and try to see the universe through genuinely alien eyes. In a way, this is a challenge we already face with other species on Earth. We share a planet with countless other forms of life, and we're still learning how to understand them, how to respect their needs and perspectives, how to coexist sustainably. If we can't fully solve that problem with organisms we're related to, organisms we can observe and study directly, how could we hope to understand beings from another world? Yet we keep trying. Scientists study animal behavior, trying to understand how different species perceive and interact with their environment. We've learned that many animals are more intelligent and more emotionally complex than we once thought. We've discovered sophisticated communication systems in whales and dolphins, problem-solving abilities in birds, social structures in insects that rival human cities in complexity. Each discovery expands our understanding of what minds can be like, what forms intelligence can take. Perhaps this work, learning to understand the other minds we share Earth with, is preparation for eventually encountering minds from beyond Earth. Each step toward understanding another species, each insight into how they perceive and think, makes us a little more flexible, a little more able to set aside our anthropocentric assumptions. Let's consider the question of time again, but from a different angle. We've talked about the age of the universe and how that relates to the existence of civilizations. But there's another temporal aspect to the Fermi Paradox that's worth exploring: the question of detection windows. Imagine that civilizations do exist throughout the galaxy, but each one has a relatively brief period during which they're detectable from a distance. For humans, this detectable period might be the era of strong radio transmissions. We started broadcasting radio signals about 100 years ago. Those signals have now spread out in a sphere about 100 light-years in radius, reaching thousands of nearby stars. Any civilization within that sphere, with sufficiently sensitive radio telescopes, could detect us. But as we've mentioned, we're actually getting quieter. Our communications technology is becoming more efficient, using less power, sending more focused signals, rather than broadcasting in all directions. In another century or two, we might not be broadcasting much radio into space at all. Our detectable period might be only a few hundred years long. If this pattern is typical, if most civilizations go through a brief radio-loud phase before their technology becomes more subtle, then the chances of detecting each other become much smaller. It's not enough for two civilizations to exist at the same time. They need to be in their detectable phases at the same time, and close enough that their signals have time to reach each other. Think of it like ships passing in the night, each one shining a searchlight for a few moments before turning it off. If the searchlights aren't pointed at each other during those brief moments when both are active, they'll never see each other, even if they're relatively close. This could explain why we haven't detected alien signals yet. Not because no one is out there, but because we're looking at the wrong time, or we were too early or too late to catch their broadcasts, or they've moved on to communication technologies we don't recognize or can't detect. The flip side of this is that civilizations might leave longer-lasting traces, not deliberate broadcasts, but artifacts or modifications to their environment that persist long after they're gone. We've already talked about Dyson spheres and similar megastructures, but there might be other things to look for. An advanced civilization might alter their planet's atmosphere in detectable ways. Industrial pollutants, artificial chemicals that don't occur naturally, might show up in the spectrum of light passing through their atmosphere. This would be evidence of technology, even if we couldn't communicate with its creators. Or they might leave artifacts in space, probes sent out to explore their solar system or beyond, satellites in orbit, debris from mining operations or construction projects. These things would persist long after the civilization that made them disappeared. If we found something like that, even a dead, inactive probe orbiting a distant star, it would answer the question of whether we're alone. Some scientists have even suggested looking for artifacts in our own solar system. If another civilization explored this region of the galaxy in the distant past, they might have left something behind. A probe in orbit around the Sun, tucked away in a stable location where it could observe the solar system for millions or billions of years. Or something on the Moon, where there's no atmosphere or geological activity to erode or bury it. The idea seems far-fetched, but it's not impossible. And it would be a lot easier to study an alien artifact here in our solar system than to try to communicate with a civilization light years away. So far, we haven't found anything like that. But we haven't looked very thoroughly either. Most of our searches for alien artifacts have been passive, relying on accidentally stumbling across something unusual. A dedicated search, using our most powerful telescopes to carefully examine asteroids and moons for signs of artificial structures, might turn up something surprising. It's a long shot, but the potential payoff is enormous. There's something deeply human about this search, about our insistence on asking whether we're alone, and our refusal to accept the silence as a final answer. Throughout history, humans have explored. We've climbed mountains, crossed oceans, ventured into deserts and jungles and polar ice. We've always wanted to know what's beyond the next horizon, what lies in the unknown places. Space is the ultimate unknown place. It's vast beyond comprehension, filled with wonders we're only beginning to understand. Black holes and neutron stars, galaxies colliding and merging, planets orbiting distant suns, perhaps even other minds wondering the same things we wonder. The search for extraterrestrial life is really just the latest chapter in the long human story of exploration and discovery. And even if we never find anyone else, even if the search continues for centuries and turns up nothing, the search itself is valuable. The effort to answer this question has driven us to develop new technologies, new ways of thinking, new perspectives on our place in the cosmos. We've built powerful telescopes that have shown us the universe in extraordinary detail. We've sent spacecraft to every planet in our solar system and beyond. We've learned to detect planets around other stars and analyze their atmospheres. We've thought deeply about what life is, how it emerges, what forms it might take. All of this knowledge, all of these capabilities, they're valuable regardless of whether we find aliens. They help us understand our own planet better, our own life, our own origins. They expand our perspective, remind us that Earth is just one small world in a vast cosmos, that the concerns that seem so urgent and all-consuming in our daily lives are taking place against a backdrop of incomprehensible scale and grandeur. There's a photograph called Pale Blue Dot, taken by the Voyager 1 spacecraft in 1990 from the edge of our solar system. In the image, Earth appears as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. The astronomer Carl Sagan, who suggested taking the photo, wrote beautifully about what it means. Every human who has ever lived, he noted, lived on that tiny speck. Every war and conquest, every civilization's rise and fall, every joy and suffering, all of it happened on that pale blue dot. The perspective is humbling. It reminds us how small we are, how fragile our world is, how precious and unlikely our existence might be. But it's also inspiring. We're part of this vast cosmos, made of the same atoms as distant stars, governed by the same physical laws. We're not separate from the universe, we're part of it. The universe becoming aware of itself, looking back at its own immensity with wonder and curiosity. Whether we're alone or not, whether we ever meet our cosmic neighbors, we're here. We exist. We've been given this brief moment of awareness, this chance to look around and try to understand what we're part of. That's remarkable in itself. When we contemplate our place in the universe, when we wonder about alien civilizations and why we haven't encountered them, we're often asking deeper questions than we realize. Questions about existence itself, about what it means to be alive, to be conscious, to be aware, about what responsibilities come with intelligence. These aren't only scientific questions, they also belong to philosophy, to meaning, to the choices that shape how we live our lives. One of the more sobering realizations that emerges from thinking about the Fermi Paradox is how fragile and how contingent everything truly is. Life on Earth, human civilization, your individual existence. All of it rests on an impossibly long chain of events that could have unfolded differently at countless points in time. If the asteroid that ended the age of the dinosaurs had missed our planet, mammals might never have risen to dominance. Humans might never have evolved. If Earth had formed slightly closer to the Sun, or slightly further, liquid water might not have existed. If the Moon didn't stabilize our planet's axial tilt, Earth's climate might have swung wildly, perhaps preventing complex life from ever emerging. Go back even further, and the picture feels even more delicate. If a nearby supernova hadn't enriched our region of the galaxy with heavy elements, neither the Sun nor the Earth could have formed. If the physical constants of the universe were even slightly different, perhaps stars would never ignite, or atoms wouldn't hold together, or the cosmos might have collapsed moments after it began. The fact that we're here at all can feel almost miraculous, as though existence itself is the product of a long series of unlikely moments that all, somehow, fell into place. People respond to this realization in different ways. For some, it feels unsettling, as if our existence hangs by the thinnest of threads in a vast and indifferent universe. For others, it creates a sense of meaning, even responsibility. If we are this rare, this improbable, then perhaps we are precious. Perhaps our existence is something to protect, to nurture, to carry forward. Perhaps we have a duty to survive, to explore, to preserve the fragile flame of consciousness that has appeared, against all odds, in this immense and silent cosmos. Philosophers sometimes express this idea through a thought experiment called the veil of ignorance. Imagine you are about to be born, but you don't know where, or when, or to whom. You have no idea whether you will be wealthy or poor, strong or fragile, privileged or vulnerable. From behind that veil, most people realize they would hope to be born into a world that is fair, compassionate, and humane. A world that protects the weak and treats every life with dignity. Because behind the veil, you might be anyone. We can extend that thought experiment outward, to the universe itself. If intelligent life is rare, if consciousness may exist in only a few places across the vast sweep of space, then all of us are, in a sense, behind a cosmic veil of ignorance. We don't know whether we are alone, or one among many. And given that uncertainty, how should we behave? What responsibilities follow from the possibility that life, especially conscious life, might be unimaginably rare? It suggests that we should care for our planet, our only known home for life. That we should value biological and cultural diversity as precious experiments in what existence can be. That we should preserve knowledge, keep learning, keep exploring, and pass our understanding forward. That we should do our best to ensure humanity survives, not only for ourselves, but because we may be the only beings in the universe capable of asking these questions at all. This is only one philosophical perspective, and reasonable people may disagree with it. But it highlights something important. The question of alien life is also a question about meaning, about value, about purpose. It is not just a scientific puzzle. It is a mirror we hold up to ourselves. Now, let's look forward for a moment, toward the long-term future, toward what humanity might become if we endure, and if we spread beyond Earth. This way of thinking is sometimes called the long-term perspective. The idea that our moral concern should extend not only to those alive today, but to all the countless generations that could exist in the deep future. If we learn to live beyond our planet, if we build stable, self-sustaining communities on other worlds, humanity's story could continue far beyond the lifespan of Earth itself. Because Earth will not last forever. In about 1 billion years, the sun will grow hotter, slowly making our planet less hospitable to complex life. And in roughly 5 billion years, the sun will swell into a red giant, likely destroying or sterilizing the inner planets entirely. But if, by then, humanity has already spread into space, the end of Earth would not mean the end of our species. Our descendants could adapt, move outward, settle other systems, carrying forward the experiment of consciousness. This vast potential future is what's at stake when we think about existential risks, threats that could end humanity or permanently limit our potential. Nuclear conflict, climate disruption, engineered pandemics, uncontrolled technologies. These risks do not only threaten those alive now, they threaten every future life that could exist, every discovery, every story, every moment of joy that might otherwise unfold. Seen from that perspective, our time in history feels unusually fragile. We possess technologies powerful enough to destroy ourselves. And at the same time, we are developing technologies that could secure our long future among the stars. The choices we make in this narrow window, in this century perhaps, may determine whether humanity becomes a long-lived cosmic civilization or a brief flicker of awareness that appeared and vanished without a trace. But our moral horizon can't stop with humans alone. If we one day discover alien life, even the simplest microbial forms, the question of how we treat it will matter deeply. Already, as we plan missions to worlds like Mars or Europa, we face ethical tensions. Should we protect potential native ecosystems from contamination, even when it limits exploration? Do alien environments have intrinsic value, simply because they are rare expressions of nature? This is the foundation of what scientists call planetary protection, sterilizing spacecraft where possible, preserving sensitive regions, balancing curiosity with restraint. And even now, that balance is delicate. If we were ever to encounter intelligent alien beings, the questions would become vastly more complex. Would we have the right to exploit their resources, to shape their world, to interfere with their development? If they were less advanced than us, would our responsibility be to help them or to leave them entirely alone? These questions echo many chapters of human history, and history shows that we have not always answered them wisely. Perhaps thinking about alien life, even before we encounter it, can help us refine our values and become a little more careful, a little more compassionate in how we treat life everywhere. And beyond science or ethics, there is something else we might gain. Every culture on Earth carries a distinct way of seeing, a lens on reality, a story about the world and our place within it. Our differences enrich us. They help us understand ourselves more fully, and encountering another intelligence, if it ever happens, might expand our imagination in ways we can scarcely begin to picture. Alien cultures, if they exist, would presumably be even more different from ours than different human cultures are from each other. They might have completely different concepts of self and society, different aesthetic sensibilities, different ways of understanding knowledge and truth. Encountering that kind of radical difference could be profoundly challenging, but also profoundly valuable. It would force us to question assumptions we didn't even know we were making, to see our own culture and values from the outside, to grow in understanding and perspective. Of course, this assumes communication and cultural exchange are possible, which, as we've discussed, is not at all certain. But even the attempt would be worthwhile. Even grappling with the challenge of trying to understand genuinely alien minds would teach us something about the nature of mind and meaning and communication. Let's shift perspective for a moment and think about the universe itself, the grand stage on which this entire question plays out. The universe is not static, it's evolving, changing over vast timescales. Stars are born and die, galaxies merge. The universe itself is expanding, with distant galaxies moving away from us, carried by the expansion of space itself. This expansion has implications for the far future. As the universe continues to expand, galaxies that are currently visible to us will eventually move beyond our cosmic horizon, receding faster than light can travel through the expanding space between us. In the very distant future, trillions of years from now, an observer in our galaxy would see only their local group of galaxies. The rest of the universe would have expanded beyond visibility. If civilizations exist that long, they'd be even more isolated than we are now, unable to even see most of the cosmos, let alone communicate with anyone outside their local galactic neighborhood. On even longer timescales, the universe will continue to cool and darken. Stars will stop forming once all the gas is used up. Existing stars will burn out. Eventually, trillions of years from now, all the stars will be gone. The universe will be dark, except for the faint glow of white dwarfs and the occasional nova, when one of these stellar remnants accretes matter from a companion. Even those will fade eventually. Black holes will dominate the far future, slowly accreting matter and growing larger. But even black holes aren't eternal. According to quantum physics, they slowly evaporate through a process called Hawking radiation, losing mass until they eventually disappear in a final burst of energy. This process is extraordinarily slow. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate. That's a number so large it's almost meaningless, a 1 followed by 67 zeros. Eventually, after timescales we can barely conceive of, the universe will reach a state sometimes called heat death. All the stars will be gone, all the black holes evaporated, all matter decayed or dispersed. What remains will be a cold, dark, dilute soup of particles and radiation, slowly approaching thermodynamic equilibrium. No energy differences will remain to power any processes. No stars will shine. No life will be possible, at least, not life as we understand it. This far future is unspeakably distant, so far ahead that it's irrelevant to any practical concerns. but it's humbling to contemplate. The universe that seems so vast and eternal, full of light and energy and possibility, is actually temporary. It had a beginning in the Big Bang 13.8 billion years ago, and it will have an ending. Though that ending is so far in the future, we can barely conceive of it. All civilizations that ever exist, whether human or alien, whether in this galaxy or any other, will play out their stories against this cosmic backdrop. We're all temporary, all brief candles flickering in the darkness before the wind inevitably blows them out. Does that make our existence meaningless? Or does the temporary nature of things make them more precious, more valuable, because they won't last forever? Different philosophical and religious traditions answer these questions differently. Some find meaning in the eternal, in things that transcend time and change. Others find meaning precisely in the temporary, in the unique, unrepeatable moments that make up a life or a civilization. There's no scientific answer to which perspective is correct. It's a question each person must answer for themselves. But perhaps there's something meaningful in the asking itself, in the fact that the universe has produced beings capable of contemplating these questions. For billions of years, the universe was just matter and energy, evolving according to physical laws, but with no one to witness it, no one to wonder about it. Then, somehow, in at least one place, and perhaps many places, the universe became aware of itself. Consciousness emerged. Minds arose that could look back at the cosmos and try to understand it. That seems remarkable, even miraculous in a secular sense. The universe made stars, and stars made elements, and elements made planets. And on at least one planet, the elements organized themselves into something that could think and feel and wonder. We're star stuff contemplating stars, as Carl Sagan put it. We're the universe looking at itself. Whether we're the only place this has happened, we don't know. Maybe consciousness has emerged countless times across the cosmos. Maybe it's extraordinarily rare, a fluke that happened here but nowhere else. Either way, it's a profound thing. Either we're part of a vast community of minds spread across the universe, or we're a lonely but precious spark of awareness in an otherwise unconscious cosmos. The search for extraterrestrial life is ultimately a search for connection, for assurance that we're not alone, that consciousness and meaning and purpose aren't unique to Earth, but are woven into the fabric of reality itself. We want to know that when we reach out into the darkness, someone might reach back. But even if no one does, even if the search continues for centuries and finds nothing, we'll still be here. We'll still be conscious, still be capable of creating meaning and beauty and knowledge. The silence of the universe, if it persists, doesn't diminish what we are or what we can do. It just means that the responsibility for creating meaning, for preserving and expanding consciousness, for exploring and understanding the universe, falls more heavily on us. As we near the end of our journey through this question, through the mystery of why we seem to be alone in a universe that should be teeming with life, it's worth taking a step back and considering what we've learned, not just about the universe, but about ourselves. The Fermi Paradox is as much a mirror as it is a window. When we ask where the aliens are, we're also asking who we are, what we value, what we hope for. There's a particular kind of loneliness that comes with being human, a loneliness that goes beyond the ordinary feeling of being apart from other people. It's the existential loneliness of being a conscious being in a universe that seems vast and indifferent, of looking out at the stars and seeing only silence looking back. We create stories and myths to fill that void, to populate the heavens with gods and spirits and meaning. Science has stripped away many of those old stories, shown us that the stars are just balls of hot gas, that the planets are just rocks and ice and gas, that the universe operates according to impersonal physical laws. But in place of those old myths, science has given us a new story, one that's just as awe-inspiring in its own way. We've learned that the universe is older and larger than our blood ancestors could have imagined. We've learned that we're connected to everything through the fundamental laws of physics, that the atoms in our bodies were forged in the hearts of stars that lived and died long before Earth existed. We've learned that life emerged from chemistry, that consciousness emerged from life, that everything we are is part of an unbroken chain of cause and effect, stretching back to the beginning of time. This story doesn't provide the same kind of comfort that traditional myths offered. It doesn't promise that we're special, that we're watched over by benevolent gods, that there's a plan or a purpose written into the structure of reality. But it offers something else: the genuine wonder of understanding, the thrill of discovery, the satisfaction of seeing clearly, even when what we see is difficult or unsettling. The question of whether aliens exist sits at an interesting intersection of what we know and what we don't know. We know that the universe is vast, that there are countless planets, that the ingredients for life are common. We know that life emerged on Earth and evolved into remarkable complexity and diversity. We know that intelligence is possible because we are proof of it. All of this suggests that life elsewhere should exist. But we don't know how likely it is for life to emerge in the first place. We don't know how common intelligence is among living things. We don't know whether technological civilizations tend to survive or destroy themselves. We don't know if the distances between stars are insurmountable barriers or just difficult challenges that advanced civilizations can overcome. We don't know if we're looking for the right signs in the right places at the right times. This uncertainty is frustrating, but also, in a way, exciting. It means there's still genuine mystery in the universe, still questions we can't answer just by thinking about them. We have to go out and look, to explore, to search, to gather data and test hypotheses. The answer to whether we're alone won't come from philosophy or speculation. It will come from observation, from patient, systematic exploration of the cosmos. And that exploration is happening right now, at an accelerating pace. New telescopes are coming online, more sensitive than anything we've had before. The James Webb Space Telescope, launched in 2021, is already transforming our understanding of the early universe, of galaxy formation, of exoplanet atmospheres. Future telescopes will be even more powerful, capable of directly imaging Earth-sized planets around nearby stars, analyzing their atmospheres for signs of life. Missions to Mars continue to search for evidence of past or present life. Future missions will bring samples back to Earth for detailed analysis. Missions to Europa and Enceladus are in development, designed to study those ocean worlds and search for signs of life in their waters. Each mission is a step forward. Each discovery or non-discovery narrows down the possibilities, brings us closer to an answer. But we should be prepared for the possibility that the answer, when it comes, might not be clear or simple. We might find ambiguous evidence, things that could be biological in origin, but could also have non-biological explanations. We might find something so strange that we have difficulty categorizing it as life or not life, according to our current definitions. The universe has a way of being more complicated than our categories and expectations allow for. Consider the discovery of organic molecules on Mars and on comets and asteroids. These are carbon-based molecules, the building blocks that life uses. Their presence tells us that the chemistry of life is not unique to Earth, that the universe naturally produces these complex molecules. But it doesn't tell us that life itself is common. Organic molecules can form through non-biological processes. They're necessary for life, but not sufficient. Or consider the detection of phosphine in the atmosphere of Venus a few years ago. Phosphine is a gas that, on Earth, is primarily produced by biological processes. Finding it in Venus's atmosphere was exciting because it could potentially indicate the presence of life, perhaps floating microbes in the planet's clouds. But the detection was controversial. Other scientists questioned whether phosphine was really there, whether the signal might have been misinterpreted. And even if it is there might be non-biological ways to produce it that we haven't thought of yet. These examples illustrate the challenges of astrobiology, the science of life in the universe. We're looking for something we've only seen once, in one place, so we don't know how representative Earth's life is. We don't know which features are universal and which are unique to Earth. We're forced to make assumptions and then test them, knowing that the universe might surprise us at any moment. This is part of what makes science so valuable, though. It's not about having all the answers. It's about having a method for finding answers, a way of questioning and testing and refining our understanding. Science admits uncertainty. It acknowledges when we don't know something, and then it provides tools for chipping away at that uncertainty, for gradually expanding the sphere of what we understand. The search for extraterrestrial life is science at its most ambitious, trying to answer one of the deepest questions we can ask. And whether we find life or not, whether we make contact with alien intelligence or remain alone, the search itself is transforming our understanding of the universe and our place in it. Let's return once more to the idea of time, because it really is central to understanding the Fermi Paradox. We exist at a specific moment in the history of the universe, about 13.8 billion years after the Big Bang. From our perspective, that seems like a very long time. But the universe might continue for trillions of years into the future, until the last stars burn out. On that timescale, we're living very early in cosmic history. What does it mean to be early? It means that most of the universe's history is still ahead. Most of the stars that will ever exist haven't formed yet. Most of the planets that could support life don't exist yet. If intelligence is common, if civilizations arise regularly throughout the universe's history, then most of them haven't existed yet. They're still in the future. This perspective suggests that we might be among the first intelligent civilizations to emerge. Not necessarily the very first, but early enough that the universe isn't crowded yet. Early enough that the galaxy is still mostly empty, waiting to be explored and settled. If that's true, then the silence we observe makes sense. We're not hearing from anyone because there isn't anyone nearby yet. We're pioneers, early arrivals to a universe that will eventually be much more populous. This is an optimistic interpretation of the Fermi Paradox. It suggests that the silence is temporary, that the future will be richer and more interesting than the present. But it also places responsibility on us. If we're early, if the galaxy is still largely empty, then we have the opportunity to explore and expand, to shape the future in ways that later civilizations won't be able to do. The choices we make, the values we uphold, could influence how life develops in this region of the galaxy for billions of years to come. Of course, this is speculation. We don't know if we're early. We might be late, the last gasp of a process that's been happening for billions of years, everyone else having risen and fallen long ago. Or we might be typical, existing at a time when many other civilizations also exist, but all of us isolated by the vast distances and the challenges of communication and travel. There's no way to know for certain, not yet. But thinking about these possibilities Considering the different ways the story might unfold helps us appreciate the stakes. The question of whether we're alone isn't just an abstract curiosity. It connects to practical questions about how we should live, what we should prioritize, how we should prepare for the future. If we're alone, or functionally alone because others are too far away to ever contact, then the preservation of Earth's life and human consciousness becomes even more important. We might be the only witnesses to this universe, the only beings capable of understanding and appreciating it. That's a profound responsibility. If we're not alone, if others are out there, then we need to think about how to be good neighbors, how to coexist peacefully, how to learn from each other without dominating or being dominated. We need to develop the wisdom and maturity to handle first contact, if it ever comes, in a way that's beneficial for all involved. Either way, the search for extraterrestrial life pushes us to be better. It encourages us to think long-term, to consider perspectives beyond our own, to value knowledge and exploration and the preservation of consciousness. These are good things to value, regardless of whether aliens exist. There's a concept in philosophy called the cosmic perspective, the idea that we should try to see things from the broadest possible viewpoint, not just from our own personal perspective or even from humanity's perspective, but from the perspective of the universe itself. What matters when you zoom out far enough that individual lives, individual civilizations, even individual galaxies become tiny details in an incomprehensibly vast picture? From the cosmic perspective, what matters is complexity, order, organization, consciousness, the universe understanding itself. These are the things that seem precious when you pull back and look at the whole. Simple matter isn't interesting. A cloud of hydrogen gas, while vast and impressive, is just atoms floating around according to the laws of physics. But a living cell, with its intricate molecular machinery, its ability to maintain itself and reproduce, and respond to its environment, that's interesting. That's the universe doing something remarkable. And a conscious being, capable of thinking about the universe, understanding physical laws, creating art and science and philosophy, that's even more remarkable. That's the universe not just being complex, but being aware of its own complexity, reflecting on itself, asking questions about itself. If life and consciousness are common in the universe, then they're part of the natural order, built into the structure of things, emerging regularly wherever conditions allow. If they're rare, then they're precious, unlikely achievements that should be protected and preserved. Either way, they matter. Either way, we should care about their survival and flourishing. This cosmic perspective doesn't erase the importance of individual lives or personal concerns. Your own joys and sufferings, your relationships and experiences, these still matter deeply. They matter to you, and that's enough. But the cosmic perspective adds another layer of meaning. It connects your existence to something larger, shows you that you're part of a grand cosmic story that's been unfolding for billions of years and will continue for billions more. When you look up at the night sky, you're looking back in time. The light from the stars takes years to reach you. You're seeing them not as they are now, but as they were when that light began its journey. The nearest stars appear as they were a few years ago. More distant stars show you what they looked like decades or centuries ago. The light from distant galaxies has been traveling for millions or billions of years. You're looking at the ancient past, preserved in light. Somewhere out there, perhaps, light from Earth is just now reaching another world. Light that left Earth years, or centuries or millennia ago, carrying information about what our planet was like back then. If anyone is watching from that distant world, With telescopes powerful enough to resolve details, they'd see Earth's past. They might see ancient civilizations, Rome or Egypt or China in their prime. Or they might see Earth before humans existed, covered in forests and oceans, with dinosaurs roaming the land. And if we're looking at them, we're seeing their past, not knowing what they're like now, whether they still exist or have vanished, whether they're thriving or struggling. This strange disconnection, this inability to see the present state of distant things, is another barrier to communication and understanding. We're all looking at each other's history, never quite catching up to each other's present. But perhaps that's okay. Perhaps the beauty is in the reaching, in the attempt to connect across the void, even knowing the connection is imperfect and delayed. Every radio signal we send into space is a message in a bottle, cast into a vast ocean, hoping someone, someday, will find it. Every search we conduct, every moment we spend listening for signals from the stars, is an act of hope, a refusal to accept that we're alone without proof. And maybe that's the real answer to the Fermi Paradox, or at least the answer that matters most to us as humans. Maybe the question isn't really, where is everybody? But how do we live with uncertainty? How do we find meaning and purpose when we don't know if anyone else is out there? How do we balance hope and realism, curiosity and caution, ambition and humility? These are the questions that the search for extraterrestrial life forces us to confront. And in confronting them, in thinking deeply about who we are and what we value, we grow. We become more thoughtful, more mature, more capable of handling the challenges ahead. As you drift towards sleep now, as your thoughts slow and soften, let yourself imagine the universe in all its vastness. Billions of galaxies, each containing billions of stars, each star potentially hosting planets, and on some of those planets, perhaps, life. Creatures adapted to their environments, evolving, surviving, maybe even thinking and wondering as we do. You might never meet them. They might never know you existed. The distances might be too great, the time too vast, the challenges too difficult to overcome. But somewhere out there, under alien skies, perhaps similar thoughts are being thought. Perhaps someone else is looking up at their night sky, seeing our sun as just another dim star among countless others, wondering if anyone is looking back. In that wondering, in that shared curiosity and loneliness and hope, you're connected. Not by communication or physical presence, but by the simple fact of being conscious beings in a vast universe, both asking the same eternal questions. Where did we come from? Why are we here? Are we alone? The universe is very old and very large and full of wonders we're only beginning to discover. Whether we're alone or not, whether we ever find our cosmic companions or remain solitary, we're part of something magnificent. Something vast and ancient and ongoing, the grand adventure of existence itself. And for now, that's enough. To be here, to be aware, to wonder and search and hope, to look up at the stars and feel that mixture of insignificance and significance, knowing we're tiny, but also knowing we're part of the universe contemplating itself. Rest now, and let these thoughts settle gently into your mind, like snow falling on a quiet winter night. The questions will still be there tomorrow. The stars will still be shining. The search will continue. But for now, there's just this moment, this breath, this peace. We're here. We exist. We wonder. And perhaps, somewhere out there in the infinite dark, someone else is wondering too. Sleep well.